Okay, so today we are doing the design of iterative circuit with an example of comparator of n bit. Now, what do we mean by iterative circuit is when something is happening again and again in one cell, whatever is happening in this cell 1 to cell n, all are same operation, but it is happening with a different set of present input, present state, which gives you present next state and present output. So we have this example of n bit comparator where it is showing the n bit is starting from x1 to xn. Two numbers will be compared, no? So x1 to xn is number 1, y1 to yn is number 2. So the x and y are being compared with each other, and each bit is being compared by one cell. So this cell is a 1-bit comparator. So this 1-bit comparator will compare x1 and y1. Similarly, cell 2 to cell n and each ith cell will be comparing 1-bit number only. But when we talk about comparison, and suppose if I want to compare, just for an example, x4, x3, x2 and x1 with I want to compare y4, y3, y2 and y1. This is a simple 4-bit number I am trying to show. And when I say that MSB is left hand side, LSB is right hand side for both the numbers, as we always write. So what do you understand? If x4 is 1 and y4 is 0, then what will happen? Does it bother about x3, x2, x1 or y3, y2, y1? It does not bother, right? So if I have a number as x4 as 1 and further all the bits as 0, suppose, and here y4 is 0 and all other bits are 1, 1, 1. So which is greater? Your x only is greater than y. So why we have to call it as iterative? Because it will be comparing bit by bit. So x4 will be compared to y4, and if x4 is higher than y4, of course the iteration will run for x3, x2, x1. It will run for all, but the result will say that x is greater than y. But if it happens that when I start comparing, it is bit by bit comparison, no? And it is a unilateral iterative circuit, what we had seen the example here. This is also unilateral iterative circuit. Unilateral means the information is flowing from one direction only. So from left to right, the information is flowing, and your final output circuit is here. We will see the design of this circuit also. And the final output of whether x is greater than y or x is less than y or x is equal to y is seen here. All this design we have to see today. So what it does, it starts with MSB. So x1 and y1 is MSB here. Of course, in my example, I have taken in an opposite way. So x1 and y1 is a MSB. It will check MSB, and MSB, the MSB of the complete number will be checked here. If the MSB are equal, the information will go to the next cell using this A2 and B2 states. That is why it is called as state. A1 and B1, A and B are used to represent the state, and X and Y are used to represent the binary number which we are comparing. So if x1, of course it starts with a 0, 0 only, and when x1 and y1, that is your MSB, if both are equal, then your A2 and B2 again will be 0 and 0. So what happens? It is comparing bit by bit. Now let me take another example. Okay, this was my example 1. Let me take another example. In that another example, let me use the same way, the way it is used in your book. So if I am comparing the two numbers like this, what does it do? It first compares x1 and y1 in cell 1, and then cell 1 says that if it is equal, it will send the state as your A1 and B1 state as 0 and 0. That means with x1 and y1, you are not able to decide whether it is greater or lesser. So the information goes to next cell, and x2 and y2 is compared then. Same way it goes on till the last LSB. And if it is equal, the information should go to the next state, because then not next state, next bit, because then next bit is the decider party now. For example, if my x1 and y1 is 0 and 0, that means whether it is equal or greater or less is not being decided by x1. Now suppose next it goes to x2 and y2, and both are 1 1. Then again greater and less is not being decided. It will be equal only. A1 and B1 will remain 0 0. I will call it as AI and BI for better understanding. So AI and BI will remain 0 0. Suppose x3 and y3 is again 1 and 1. It will again remain at 0 and 0. Now, for example, suppose rest all bits remained like that. Let us go to the last bit and imagine that xn became 1 and yn became 0. So now what happens? It says that AI and BI will no longer remain 0 0. AI and BI will be changed. AI and BI will be changed to the case where your second bit is higher, means second bit is greater. So when your y is greater, it will be showing that your the state will depend how we are taking it as. Suppose I am taking my y as higher, the state may change to this 0 and 1. And if my x is higher, the state will change to 1 0. So on. And of course, there is no 1 1. There is no 1 1. This is don't care. So the state will transfer the information. So that means if it will start with a 0 0 only, it will compare x1 and y1. If it is 1 1 or 0 0, means a2 and b2 remains equal, means 0 0. And this goes on till the end, and then I will have a output circuit which will decide that if one of the input, that is if x is greater than y, z3 will be made high. If x is less than y, z1 will be made high, and z2 will be made high if neither of this is 1. So this is the general block diagram of a iterative circuit. But do you think that I will be using so many 1-bit cell? We do not do this. Now in this example, we are planning to check that only. Okay. So now I have explained you what do you mean by your present state, your next state, your input, and your output. Now in this case, you can see in all these n number of cell, you do not have any output at cell level. At cell level, you have only state transfer through A and B, and your input is coming as x1 and y1 or xi and yi. Your output is decided by the output circuit only. So what do we understand? We understand that this Z1, Z2, Z3 is high. You can see here you have 3 output, but you had only 2 input. So this circuit also we will be designing. But you can understand now to design your state table with all the given information. Now to design the state table, let us start. We will see what all is required to make a state table. So I am making a state table of the comparator. State table of comparator. Now you write down all the conditions along with me. so that there is no confusion. Okay. Now, as I already told you, state will be decided by A and B. But as we are in habit of writing our state with S, let us do that only. So this A and B will be giving me my present state, that is SI. I will write here also, this is my present state, and your SI plus 1 is nothing but your next state. Okay, and you know that your next state will depend upon present state as well as present input. Why I am saying this? Because if I have a present state as 0 and 0, present state as 0 and 0, that means both were equal till now, and present state suddenly says that yi is higher than xi. So next state will depend upon my present state, whether it was equal or not equal, and my present input, that is my x and y are equal or not equal. I hope I am clear. So now you have to see your present state, next state, and next state is decided by the inputs, and your input is xi yi. Okay, xi yi. And suppose I am taking, how many possibilities will be there with the two inputs? There will be 4 possibility, right? So I am writing all the 4 possibility here. So this is my xi and yi. All of you please note down along with me and understand also. So xi, yi. So I have 4 possibility of my inputs. I have 4 possibilities of my input xi and yi. I need to take care of all those things. And when I talk about my present state with the given information, you understand that present state also there are 3 possibilities. Number 1 possibility is when x is equal to y, and I will call it as S0. Second possibility is when previous input says that x was greater than y. And the third possibility is when previous inputs give me the state that my y was greater than s. Now, very important thing to understand here. I hope all of you will pay attention and understand. When my previous state says, when my previous state, and this previous state can be anywhere here. Anywhere here means I am talking about this A1 and B1 only. AI or BI or A and B and anything. So I am talking about my A and B. My A and B says that my previous data means whichever is my current input. Previous to that, my inputs were equal, and that is why I was in equal state. S0 is equal state. Now, who will decide when my previous states or my present state says that it is equal? Then who will decide my next state? Only my input will decide whether my next state will make it greater or lesser. So now let us start. I imagine that I have all my previous MSBs as equal. Now my current input says it is 0 and 0. Xi is 0, yi is also 0. So what happens? Is it equal, greater or lesser? It is equal, greater or lesser? Tell me. It is, if my both x and y are 0, 0 means it is equal. Yes or no? It is equal. Same way, when I say xi and yi as 1 and 1 means both are equal. So it was equal, it remained equal. It remained equal means it will remain in S0 state of equality. Now, if I say that yi became 1 and xi is 0, then which one is greater in x and y? Which one is greater in x and y here?
Y is greater, ma'am.
Correct. Y is greater. Now, when y is greater, y greater state is defined by S2. Can you see here? Y is greater than x. So, y greater than x is being defined by S2. So, if xi is 0 and yi is 1, then my state changes to S2 and y becomes greater. Same way, if I have the opposite case, if I have,
S1.
correct, if I have opposite case where it says that xi is 1 and yi is 0, then it will take x greater than y. So it will go to S1, right? And correspondingly, when you have your output equal z1, z2, z3 also we need to decide. In this case, when z2 will be higher, when z3 will be higher, you can see that when your s0 was equal, then in this diagram we will have to see z2 is denoted for x equal to y. Z2 is denoted for x equal to y. So in this case, your Z2 will be high, and uh, your Z1 is denoted high for y greater than x. Y greater than x. So y greater than x means which one it was? Z1. Y greater than x means it will be here, and in this case it will be here. So your output is being decided by your present state in this case as of now. Now coming on to your next row. What does next row say? Next row say that in the previous MSB only my x is greater than y. So what do you think your next state should do? If my MSB only says that x is greater than y, does my present input decide anything? It is this case only. When my MSB said that one number is higher than other number, then these things does not matter, because in binary number, MSB plays the major role for comparison. So when already my x is greater than y based upon my MSB, my present input of x and y does not matter. Already my S1 or already my x is greater than y and it has gone to S1 state. So once it has gone to S1 state, my present input does not matter. So for all the cases, my present state will be equal to my next state, and all the cases it will remain at S1 once one MSB has proved it to be higher than y. Same way for S2, what happens? My y is higher than x based on certain MSB, whichever MSB it be. And when MSB says that it is higher, like in this case only example 1, if MSB says that it is y is higher, now no LSB can play any role and it will remain in S2 state, which says that Z1 will be high and your y is greater than x. So this is your state table. This is your state table. And if you remember in my diagram, we had told that state will be decided by AI and BI. Inputs are decided by xi and yi, and output is again your z1, z2, z3. I may change, but output will always remain 3 as less than, more than, or equal. Okay, now we have again come in the form of state table. So when we have come in the form of state table, this is something which you know already. Okay, so now what we will do is S0 is decided by AI, BI as 0 and 0, and S1 is decided by 0 and 1, and S2 is decided by 1 and 0, and 1 1 is don't care, 1 1 is not there. So let us quickly finish it because you need a generalized circuit also. I hope you have copied the state table. I will be converting quickly because this is something which you know already. Okay, I'm now making the transition table. I'm making the transition table. Your state table is copied completely, I guess. You can take a snap of this and you can copy it. Okay.
Completed, ma'am.
Okay. So now let us write our state transition table, which you people know very well. I want you people to do on your own. Okay. This is your present state. Sorry, present input. Present input. This is your output. And as I had given the naming ceremony as 0, 0, 1, 0, 0, 1 and 1, 0. And for the present state as 0, 1, it remained at state 1. For state 2, it remained at state 2. And for equality, it remained at equality. And for greater, it changed the state. It changed the state, and this is simply copy of the previous table. Okay. Now, quickly we have to see our K-map. And I am writing AIBI as MSBs here. What are the inputs? What are the inputs for this? Input is present state and present input, right? So present state is taken as MSB as AI and BI, and present input is taken as LSBs of XY and XI and YI. Now very quickly you should see that how to write this. So what you can see is 0, 0, 0, 1 and 1, 0. Of course it is coming here. So which column will be don't care? Which column will be don't care? Which row will be don't care?
1, 1.
Yes, because AIBI 1, 1 is not available. So this complete row will be a don't care. Okay. Now, next what I have to do? AIBI is 0, 0 and XIYI is 0, 0 here. Means what? This will be denoted by this. Now let us check the complete thing and copy it. So tell me where and all what I have to write. This is your AI, BI, AI plus 1 and BI plus 1. I am writing this specific for AI plus 1 and one more I will be writing for BI plus 1. So your AI plus 1 is AI plus 1 is this, right? This is your AI plus 1 and BI plus 1 will be your second column. This is your BI plus 1. So we need to write BI plus 1. So because this is something which you people know, I want you to tell me where and all I have to put 1. So I'm waiting for your answer. You should be very fast now for all these things. You can't take more time because time management is also important in exam. So this row will be don't care here also. Yes. So tell me what should I do? Your AI plus 1 is 1, 1, 1, 1 in this full case, right? AI plus 1 is 1, 1, 1 in full this case, and AI and BI is 1, 0 here. So that means what? This complete row will be 1, 1, 1, right? So this complete row will be 1, 1, 1, and only one case of 0, 0. That means this one. Only one case of this 0, 0. Here 1 is there. So where is that? That is 0, 1. Where is 0, 1? Here. So you will have 1, 1 here also. And rest all will be 0. Rest all will be 0. In the same lines, here where should be the row of 1? Where is row of 1?
second row, ma'am.
0,
Correct.
1.
Right. So your AI BI is here 0 1, and your BI plus 1 is 1 1 1 in this 0 1 row. So this 0 1 row will be fully 1, and one more case of 0 1 is here, which is when your 1 0 is high. XIYI is 1 0. Here is your XIYI, which is 1 0. So this one is high here. Of course, I am doing the shortcut business. You can see your table in leisurely, you can see and you can find. Okay. So what do you see? You get which all grouping you are getting? You are getting here this one big group and one pair, this, right? Here you get your one this group, and you get your, you can take your pairing here only. So what do you get? You get AI plus XI dash YI BI dash. Okay, this you people know, so I am not asking. I am assuming that each one of you are able to do it on your own. Now I am writing K-map and getting equation, that is fine, but you can understand this equation otherwise also. What you can see here is AI plus 1 will be equal to AI. This is the case when MSB only says that your one specific input is high. So if this is 1, your xi and yi will not be dependent upon. AI plus 1 will be 1 if AI is 1. And if AI is 0, that means from the previous bit, from the MSB, AI plus 1 is not high, and if this is 0, then it will depend upon your present input. And present input will make AI plus 1 high only when your Y is high, and this remains 0. And BI dash means what? That AI is 0 from the previous case, and BI is also 0 from the previous case. That is why that BI dash is coming here. Okay, you can understand the working of your comparator with this equation also. So this equation will give me typical cell for comparator. Typical cell means what? I am talking about the design of this cell. Cell 1, cell 2. I am talking about this cell only. So the design of this cell, okay, I have here, I need not draw. I will show you. See, this is your state table for comparator, and this is your K-map, and this is your typical cell. What is this typical cell? It is making equation of these two only. So AI and BI is your present state. That is why it is coming from left direction. XI and YI is your present input. That is why it is coming from top. And this is your equation. What is making your, this one, AI plus 1 is what? AI plus 1 it is. So it is AI dash and BI dash plus AI dash, and here you have your XI, YI and BI dash. So you can observe this circuit. This circuit is depicting your this equation only, right? Now this completes your cell design. I hope you have understood. What do you see in this box is your cell design of this, where your AI and BI is your present state, XI and YI is your present input, and the cell will decide your next state, that is AI plus 1 and BI plus 1. So you can see here that is the your one cell. So these cell will be connected iteratively n number of time. After that, next job for you to decide is your output circuit. Now output circuit is done like this. What you can see is if AI and BI both are 0 0 or 1 1, then this XOR gate will give you high, showing that Z2 is high and X is equal to Y. And otherwise, if if ai plus 1 is giving you high, means your x is less than y, and if this is high means your y is less than x. This is with general understanding we can do, but without doing general understanding we can do with k-map also. Now let us understand this k-map. This k-map, what does it do? This is talking about bi plus 1 and ai plus 1. Here they have written n now. That is not a problem. It may be I, n, anything. So what it is trying to tell here is that when a is greater than b. So this is this case. Can you see? When a is ai plus 1, ai plus 1 is 1 and b is 0. So this is high, and 1 1 is don't care. I hope you remember. 1 1 was don't care, na? ai bi 1 1 was don't care. So that is why this 1 1 is don't care. Put in all the three cells. Now z1 will be high, that is when y is greater than x is happening with the case when your a was 1 and b was 0. Now we can again check here. When a was 1 and b was 0, when a was 1 and b was 0, that was given to a case when x is greater than y and z1 is 1. So this is the case when it was given the value for x. You should understand that you should not confuse your xy with ab. Okay. So when a and b is 1 and 0, output is saying that it is directly connected to z1 and it says that y is greater than x. Opposite case, when your b is 1 and a is 0, this is of course don't care again, and that can be directly connected to your b. And the third case happens when neither this is high nor this is high. That is the case when a and b both are 0 and 0, depicting the equality state. So equality state, 1 will come here. So then you can see when you circle these two, it becomes a XOR operation. So that is why your XOR operation is this. So this is your output circuit. Now you remember we had cell circuit and output circuit. So cell I have made you understand now. This was your cell, and output circuit is XOR gate. Simply you put one XOR gate, that becomes your output circuit. So this is your cell and this is your output circuit. Now next thing, if I tell that I want a 10-bit comparator, you will make such 10 cells, right? Now suddenly I say, no, I want a 15-bit comparator. Then what you will do? You will bring such 15 cells. Is it practically possible? It is not. It is practically impossible to use such 10-bit 10 times or 20 times or n number of times. So we have a simplified application circuit, which is this. Now see in this what is happening. Your output circuit remains same. Output circuit is nothing one XOR gate. So it will give you x greater than y, x less than y, and x equal to y. Output circuit remains same. What we are doing? We are having only one such cell. We are having only one such cell. What is your typical cell? Typical cell is this only. Typical cell connects your present state to next state with the present input. So the typical cell remains here. What is happening now? Your previous state comes like this, compares your ith bit, it goes to D flip-flop because it gives you one cycle delay. Present cycle it will be here, after next cycle it will go here. And the same typical cell will be using n number of times for n-bit comparator. So this is your sequential comparator of binary number, and in any iterative circuit, we never do n number of times connection. We use typical such thing at 1 and we use this cell n number of time. Now, because it is a sequential circuit, all the bits can't be bombarded to this typical cell at once. It will not be possible to do. So what does it do? It compares 2 bit, gives the output. That output is checked. We give some time means 1 clock cycle time. it goes back here and then it will check with the next bit of input. So then next bit of input will be keep on supplying here. Now there is no restriction. You can ask for 10-bit comparator, 15-bit comparator, or 100-bit comparator also. That does not matter anymore. With one D flip-flop here and one typical cell, your n-bit comparator circuit is ready. This is an example of comparator only. Like this, we should be able to design any n-bit iterative circuit for any such application using our state machine, state logic, and state table. Okay, so this completes your iterative circuit. Any doubt, you should ask me.